Good morning, everyone.
Good morning, sir.
Good morning. We start with the recording first. So I hope you are able to see my screen.
Yes, sir.
Yes, sir.
Okay, thank you. So any questions from the previous lecture? All right. So let's begin. So we basically started looking at the compilation steps um, that GCC compiler goes through, right? So we are learning this so that we understand that where do we start in the C program, or when we write the C program, what are the steps it takes to take your source code and go all the way up to the executable file. Right, so how the executable files are created. Also, we know that you could have multiple source files, multiple C source files and header files that you could be using that can get converted eventually into the executable file. So how does the handling of these multiple C files are done to create a single executable file? So all of that process we will be studying in this particular chapter. Um, so anybody has a question? Okay. So these are the four steps. Briefly, we looked at it in the previous lecture that we go through the pre-processing steps. Then we do the compilation, then we do the assembling, and then we finally do the linking. So these are the four steps that GCC follows in order to generate the executable file from the multiple source files and the header files. So first step is the pre-processing. So what is the pre-processing step? Now, today I was having some issue with the virtual machine. So what I've done is I've actually had to copy the files on my local machine in order to execute them. I'm not able to map the Windows drive, but anyway, I have copied the files here, and so the files are available here. So we'll actually look through those files from the virtual machine here. So in the hello world.c, we see that there are various pound sign commands that we have used, right? So these pound sign commands are basically called preprocessor directives. So what is the preprocessor directive? Preprocessor directives is nothing but the commands that are taken care by the preprocessor. So the first tool that GCC uses is what is called preprocessor, and in the binary file or the executable file for the preprocessor is called CPP. How do I know that? Because when you go to the terminal window and when you say which CPP, it will tell you that the CPP is the program that is located at this path, right? So user bin CPP. So as long as your CPP is in a path with the path variable. So for example, when I say echo $path, right, you will see that user bin folder will be here, right? So user bin folder is over here. So what it did when I did which, right? When I did which, basically what it did, it looked for this. 1 second. Sorry. So
Sir, sorry to interrupt, but your screen is not much clear from the last. The issue is from the last lecture also, right? In the last lecture also, the screen was not much clear. It is. and
So you're
his
not able
lecture
to
is
see the
also.
screen? You're not able to
Yes,
see the
sir.
screen?
No, we are able to see the screen, but the letters are not clearly
Like
visible.
it
Like
appears a little blurry.
Yes,
So
sir.
the large letters are visible, but the smaller ones are not clear. They are hard to see.
Sir, I
yes,
guess
sir.
the screen is appearing at both end. Like you are sharing the screen, and in your camera also the screen is also visible. So probably that.
Okay.
So, so you can, I guess, turn the off the camera.
Turn off the camera. Okay, sure. I'll do that. How about now?
Now the screen is also not visible.
Yeah, sir. Screen is also not visible.
Okay, so I basically turned off the camera, or um, okay. Let me see. Maybe I need to change the layout. About now?
So actually the layout would be visible on your end only. So like we see no difference.
So I put the layout to auto. Um,
So
if
I
I
guess
do
you can reshare the screen. Like
let me stop and then about now?
Yes.
Better? Is it better?
So it is blurry.
No, sir.
No,
It
sir.
is blurry.
Okay, blurry part. Uh, Basically, what happened was a couple days ago, I had to upgrade it to Windows 11. So I don't know if that is causing any issue. Uh, Let me do one thing. Let me change the resolution of my um, screen. Maybe that is an issue. Is it better? Okay, let me scale 100%, and then I will change this to 1280 by 1024. No. Is it better?
No, sir.
Sir, actually,
Huh.
there's some kind of error or bug which when you share the screen, it automatically shows in your camera also, like your front camera. There's some
Achha.
bug. That's
Yes,
why,
sir.
that's why it's the problem.
Uh,
Screen resolution is not the problem, sir.
Acha. Okay.
So while sharing, you can only share the tab, so, only share the window.
Yeah, but we need the presentation and the virtual.
Yes, sir. That's
That is
what.
the only problem. So I can't, if I share just the one window, then you won't be able to see both. That is the only problem. If only presentation would be needed, then I can just because of the Windows 11 upgrade or something, maybe some because I tested with virtual machine and I tested general Google Meet, but obviously I couldn't see what you guys are saying, so that's why maybe there is some setting which I need to figure out what to do with. But I guess for now, we'll continue to use this companion mode and hopefully you'll be able to see it. Okay. So, so CPP is the processor. That is what we use. And when we, when we run that program, it basically runs only the processor, pre-processor part. Okay. If you want to do the same thing with the GCC compiler, you have to use -e switch. So what -e switch? So basically, GCC compiler, it does not actually have the all the steps included in it. It is an envelope. So GCC is the utility or kind of a program which calls other utilities. Like for example, CPP is one of the utility which does the pre-processing step. So GCC internally calls CPP. Okay, and just to call the CPP preprocessor from GCC, only to run that step instead of doing all the 4 steps, you use -e switch. Now, what is the purpose of doing the pre-processing, right? So first thing we know that when we, sorry, going back here. So we know that when we look at the C files, right? We have the header files, and then we have these, hash def and hash define and all those kind of preprocessor directive. So the purpose or the function of the preprocessor is first to expand all these header files. So all the code, all the forward declaration of the function and the global variables or structures or whatever is defined in this header file, it will have to be included in the source itself, right? So instead of using the header file, it will skip using the header file. Instead, it will take all the code from the header file and include it over here. Similarly, if you have the defined, the constants that are defined, for example, if you have done hash define and then IE is 1, whatever, right? So this is my constant, which I'm defining with the value 1. So this part will be taken care by the preprocessor. Similarly, here what it is doing is, it is checking whether the Intel constant is defined or not. Intel keyword is defined or not. Okay, so we don't have any Intel keyword here, but if you go to this header file, right? So I've included this header file here. And if you go to this header file, there is an Intel constant defined here. So basically what will happen is when it expands this header file, it will include these 2 parts also in my source file, right? And therefore this Intel constant will be defined. Okay, and based on that, it will say that whether this model string has to be declared like this or it has to be declared like this. So if the Intel, it is able to find the constant Intel, if the Intel constant is defined, then the model string will be initialized with the string Intel. Otherwise, it will be initialized with the other. Okay, so these are the preprocessor directives that it takes care of. And this is what the preprocessor function is. Now, when we run the preprocessor, what basically it does is it actually, we have to, the output is actually displayed on the screen, on the standard output, right? So what we do is we actually use a redirection operation, right, to capture the standard output content into this .i file. So .i file is the generated output from the preprocessor. Okay, that is what the step we are going to run. So let me run that. So we are going to say CPP hello world dot c greater than hello world dot I. Okay, so this .i file is created, and I can go to the folder and I can open that .i file, which should be here somewhere.
Sir, in center.
In center. Actually, I'm just trying to change the display so that Okay, but how do I get the details?
So 50%.
Yeah, but this will just change the size. I want to list it in the detail format. And I know there is a way to do it, but anyway, let's just, oh, yeah, because I just did the date-wise ordering. So here you will see that all of these content is coming from the header files. Okay. So if you look at this content, these are all the header file that is extended or that is expanded and included in my source file. Right. So all of this stuff is coming from all the different header files that I have. Now, if you look at this part over here, right? In my header file, which is this one, sorry, not that one. In this one, I have the Intel keyword defined, right? And so when it executed this if statement, it found out that the Intel keyword is defined. So it actually used this definition. So when I look at my .i file, right? Let me actually bring that in the front. So when I look at this definition, you will notice that I have the Intel initialization of the model variable with Intel because that constant is defined. If I comment this line out, right? If I comment this line out, save the header file and save the hello world C file and then compile again, right? And then compile again. Sorry, going back to the. And if we open that, sorry, if you open that file again, reload, you will see that now it is initialized with other. The reason being that this constant is no longer defined anymore. So when the preprocessor executed this step, it did not find the constant. Okay, and therefore it actually used this particular definition. This is how the preprocessor handles these if statements. Okay, all the other header file stuff, it is basically included in your .i file, and that you will be able to see over here. Okay, you will be able to see over here. So all of these are forward declaration of the function, some of the global variables, because there are two header files I've included here, stdio.h and math.h, and there is one header file which is the string.h I've included in my header file. So those are all included over here. So this is the function of preprocessor step. But if you look at the actual source code, right, the original source code, there is no change here, right? So the main function remains exactly the same. There is no change here. Okay. So the basic work that preprocessor does, it handles all these preprocessor directives using that starts with the pound sign. It includes all the header file content. It takes care of this if def kind of conditions and also the hash defined constants and so on. Right, that's all it does. Okay, so that is about the preprocessor step. Now, once we have the .i file, right, we follow the next step, and that next step is basically your compilation step. Okay, so compilation step takes the .i file as an input, okay, or preprocessed file as an input, and then it generates what we call assembly code. Okay, so assembly code is the code which is specific to a processor that you have in your computer. So each of the processor, for example, Intel makes several different kind of processors. AMD company makes different kind of processors. ARM-based processors are also available widely, right? You have a lot of devices such as Raspberry Pi or BeagleBone, even your mobile phones, and some of the servers or even the computers, does have the ARM processor. So what happens is, for example, if you buy a Mac, right, Mac will have ARM-based processor. So those processors also have a specific assembly code. So assembly code is specific to your processor. And therefore, once your pre-processed file is compiled into the assembly code, that assembly code you cannot run in any other computer, but the one which has that specific type of processors. Okay, so that is the machine dependent code we are talking about. So until the pre-processed file, it was machine independent code, because you can take the pre-processed file and move it somewhere else, and then you can still run your compilation step to create an assembly code. But once the assembly code is created, you cannot actually run that assembly code or take that assembly code in another type of computer, right? Unless that computer has the same processor, same kind of processor as your computer has, then it will work, right? But basically, if it has a different kind of processor, then this code will not work. Okay, that is what we are talking about. So compilation step basically takes, so compilation is done through a compiler called CC. So again, GCC internally calls CC as a compiler. And -S switch basically says that stop only at the assembly code. So there are two steps your compiler will do, but it will basically stop at generation of the assembly code. So you generate an assembly code using the pre-processed file. So let us run this step, and then I'll show you what that file looks like, right? So again, if we do which CC, it will tell you that CC is the program which is available in your user bin. So I will do which CC and then hello world.i, which is my pre-processed file. Now, when I do that, you will notice that there will be a .s file that will be created. So here is the .s file that is created, right? And so when I open this file, let me do gedit. So this is the code, that is the assembly code. Okay, so you will see, I mean, if you don't understand the processor programming, you won't be able to really understand in detail what these instructions are. But just so you know, these instructions are, let's say in my computer, I have Intel Core, I think it's a quad core processor, or no, 6-core processor, 12 threads, right? So it's an Intel based processor. And so these instruction sets are for the Intel processor, right? So if you look at some of these instructions, it makes a little bit of sense. So for example, this LEA stands for load effective address, right? So from the memory address which is available in this register, it is going to load a data, right? Then move basically says that take the 0 value and move it into this processor register. So each processor, depending on the architecture of the processor, you can have 16 registers, you can have 32, 64, 128. Some higher end processors may even have more registers in them, right? So register is the closest memory area which is inbuilt into the processor itself. So you are taking some value and putting into that register, and then you can see that when you look at your C file, right? So again, let me move this towards the starting so that we can kind of compare, right? So you will see that we have a printf here at the beginning, right? And then we have the power function we are calling, and then again we have a printf function. So if you look at your assembly code, that's what it looks like. So call is basically calling to this printf function, right? In terms of assembly code, it is called subroutine, right? So we are calling the subroutine called printf, and call is the assembly instruction to actually call the subroutine. Okay. Then you will see that there will be another call to this power subroutine or power function, and then there is also another one for printf. And all of these these instructions are meant to get the data required to be passed to these functions. So that is what it is doing, right? So this is basically your assembly code, right? this is still a human readable code, and we are able to still read this information, right? And if you study the processor assembly language, then you can still kind of make a heads and tails out of what it is trying to do. So the people who actually work in the processor architecture area, they really understand how this exact code is working. Okay, and we can also kind of make sense of it, right? So now, yes. Do you have a question? Okay. So this is how your assembly code looks like, and this is how we convert that C file into a preprocess file, and then preprocess file gets converted into the assembly code. So you can also invoke the the compilation step or CC compiler using the -s switch on the GCC, right? So either one of these command will work. Now, once you have the assembly code, what you are supposed to do is you are supposed to create an object file. An object file is nothing but a binary file. Okay, so basically your object file is taking your assembler. Assembler is the program again. AS is the assembler that we use. So when I go back to which AS, right? So this is my assembler program, and assembler program takes the assembly file as an input, and it will convert that assembly code into the binary file, right? So this object file is a binary file, and unless you have a binary editor, you cannot actually view this file. Okay, gedit will not allow you to, I mean, you can view it, but you will not be able to make sense out of it because it will all be gibberish characters, right? You won't be able to read it. This is the exact binary file which you can actually run on a computer unless the linking step, right? So linking step is the last one which is left to do, but the object file is actually almost equivalent to the executable file. What is the difference between the object file and the final executable file? What happens is, let's say if you have called a function from your program, right? The object files does not know what are the addresses of these functions. Okay, so function addresses are not yet known until the time you do the linking. So linking is the last step that we will look at. But for now, in the object file, all we do is we take the assembly code and convert it into the object code, which basically is the binary code for the assembly, right? So let's run this step. AS hello world.s -o hello world.o, and that's it. So when I look at this file, there will be a .o file created, right? And this is going to be a binary file. So if I look at this file, you can see what it looks like. So these are all hex code, hexadecimal code which are displayed over here, but we exactly don't know what it is, right? Because you have to be really able to open this in the binary editor or hexadecimal editor, and then you have to actually see unless you work for that processor architecture, you will not actually know that which of the assembly instruction is converted in which format, right? Now there is another way to take care of that, and that is what I have shown here in the bottom part. So basically what happens is that when you have your object file, right, you can do what is known as reverse engineering. Okay, what is reverse engineering? Reverse engineering means that you take your binary code, okay, and then convert it back into the assembly code. Okay, so you take your binary code, which is the .o file, and convert it back into the assembly code, and this is the command to do that. Okay, so let me run this command. So it's going to be obj dump minus d minus m intel minus s and then the enter is capital or lowercase. Hello world dot o greater than. So again, here we are just using the redirection because the again, this file name can be anything. I mean, you can say, you know, instead of assembly, you can put some other thing also, extension, it's fine. This has to be the .o file, and greater than this file, again, as we know, it's a redirection, right? So standard output redirection. So it has created this file, right? And I'm going to open that in the gedit. Okay. So if you look at this file, okay, so this is my assembly code equivalent to what is there in my object file. Okay, so it is saying that I've converted my this object file contains the assembly code using the x86 assembly instruction. x86 normally, well, x86 instructions, assembly instructions are used in Intel-based processor as well as AMD-based processor. If you have an ARM processor, it would have a different code over here. Okay, and then these are, as you can see, these are the you know, assembly instructions that we have seen in our original assembly code, right? But then there are some information here also. So what these are is that these are the equivalent hexadecimal codes of this assembly instruction. So what happened was, when you ran your assembler on the assembly code, what it did is it took each of these assembly instructions and converted into this hexadecimal format. Okay, so converted them into this hexadecimal format, and that hexadecimal format is your binary code. That is what was put into this .o file. Okay, and these are the absolute addresses, memory addresses. So we are saying that you start loading the code at the address 0, and then it requires these 4 bytes. Okay, then at the 4th address it requires a single byte. At 5 it requires these 3 bytes, and so on. Right. So each of these are the memory addresses, and then this is the equivalent hexadecimal code for these assembly instructions. That is what this is. Okay. So I've shown you that you can take the assembly code, convert it into the object file, and then you can take the object file and sort of convert it back into the assembly code, equivalent assembly code. And each of these calls are again for the 3 functions that we have called, right? So this would be for the first printf, this would be for the power, and then this would be for another printf, right? So that is what we have, right? So that is how we can actually see the information back into the assembly. Now there is an additional, you know, if you instead of running the assembler separately, right? If you use a -c switch with the GCC compiler, right? What it does is it runs 3 steps: pre-processing step, the compilation step, and the assembling step. So these 3 steps are executed when you use -c switch with GCC. Okay. Now, so you can actually do that with the -c switch, and then -g switch of the GCC compiler puts some additional debugging information in the object file. Okay, so when you do -c, it will not create a .i file, or it will not create .s file, intermediate files, but it will do all those steps, and finally it will just create .o file. So from the .c file, it will directly create .o file. Okay, but that .o file will have some additional debugging information, and using that .o file, if you run the step, you will be able to see some extra information in your assembly code. Okay, and let us do that. So I'll actually compile the same code again using that option. So GCC -c hello world.c, and I need to use -g here. Okay, so now if you see, I have the .o file here, which is the newly created, and now if I run that assembling step, this one, okay, it will create again a new assembly file, right? And now if I open this file in my editor, sorry, this one, okay, so you see that there is some additional information that you are seeing. What you are seeing? You are seeing that these are all the introductory part, meaning that taking command line argument and stuff, that is what is done here. Now the printf, right, printf statement is executed in these lines. So it is saying that this was the line in the source code, which is then equivalently converted into these 4 lines. Okay, then it is saying that your variable declaration and initialization are done in these 2 lines. Okay, then you are calling a power function, which is then done using these lines. Okay, this is to store the result back into the C variable, and then these are the reading of the variable a and b, right? Passing the variable a and b to the function. And then this one again is the printf, which is then taken care over here, right? So this is basically what the assembly code would look like with the functions here. Okay, so this is what you can actually see, that how your C source file is converted into the assembly code and finally converted into the binary code. Now, as you can see, that .o file is created for each source files, each C file. Okay, it means that if you have multiple C files, for each of those C files, there will be a .o file created. Okay, and what will happen is that when you create a .o file, it may not know exactly where the functions are located in the memory. Okay, where the functions are located in the memory. So it will kind of put some dummy information here. It will basically put approximate information here, that there will be some address that will be provided over here. Okay, and that address will be provided at the linking time. And that is the last step that we do, which is the linking step. 1 second, let me just drink water. Okay, so what we know that we use stdio.h header files, we use maths.h header files, and we use the printf, scanf, those kind of functions in our program, right? And if I remember correctly, somebody had asked me that where the code of those functions are, right? Where the code of those functions are. So what basically happens is that until this point of time, until the linker step is done, the program doesn't know actually where the code of that function is. Now that function code is there in the library file, which would have been loaded into the memory, and the address of that memory where the function is loaded has to be included in your executable file. That is what the linker does. Okay, so that is what the linker does. So LD is the linker program, which basically takes care of that. Okay, so LD is the linker program which takes care of that, and basically when we create an executable file, so when you pass the .o file directly to the GCC compiler, it knows that you have already done the first 3 steps, right? You've already done the pre-processing step, the compilation step, and the assembling step. Okay, so the only thing that is left to do is to create an executable file. So when you run GCC by passing the .o file, it will basically create your executable file. Okay, by default, as I said, it creates a.out, So when I say GCC hello world.o minus, if I don't provide minus o option, right? Okay, so it find POW is not there because we didn't provide the library where the POW is there. So I have to use, so what happens is that all the functions that we use in the stdio.h, right? So that library file is by default included in the linking step. So the linking step already knows that most of the program or all of the program will use stdio.h file. So all the functions which we use from the stdio.h file will be automatically be included in your executable file, or it will find those functions printf and scanf and stuff like that into a relevant library file and include it in the executable file. But the math.h, which is what we have included in our code, right, in our world.io, in our helloworld.com, right? So we've included, go back. So we've included this power function. Power function is available in the math library. And by default, math library is not included in the linking step. So you have to tell the compiler to include the math library to find this power function. And for that, we have to use -l switch. Okay. So you can do man gcc, and then if you do -l, it'll be hard to find because it has a lots and lots of options. Okay, it should be here somewhere. I guess you will have to take my word. It's a very long man.
Sir?
So, yeah.
Sir, try to find -l space.
Minus
L plus space.
You were able to find it? You were able to find it?
See, it directly shown -l space.
So it was just
Yeah. So here it is, right? So -l object C or -l library. So you can see that, right? So it says -l and then library file name. So you can provide a library file name here, or you can do without the space also. You can provide that library file name to say that which library you want to include, right? So, or you can provide the object file. Okay. So -l switch basically allows you to provide the library information. Okay. And locate lib m dot a. This is the library file where the math functions are. Okay. So usually what happens is whenever we create a library file, and when we create when I'll show you how to create our own library file, you will understand more about this one. But basically what happens is that the library file name is just this word after the lib. So lib is sort of like a prefix that we have to always use for the library files. Okay. And then there are two types of library files, static and dynamic. So .a is the extension for the static library. .so is the extension for the dynamic library. So we are looking for a static library here, and it is a lib is the prefix for the library file name, and then m stands for math. Okay, so this is the math library that we have to include in our compilation in our linking step. Okay, once we do that, then we will be able to find the POW function. Okay, so in order to do that, I think there could be also SO file. Yeah, so there are some SO. You can see that there is also a SO library file. So the linker step will try to find either one of them. If you don't provide the exact file name, if you provide the exact file name, then it will link only that file, dynamic or static. But if you don't provide the exact file, it will try to find whichever one it is available, and then it will link that particular one. So the way we are going to do for now is I'm going to just say hello world.o, and then I'm going to say -l m. So -l switch basically says that I want to link a library. Okay, and when I just provide m keyword, it basically says that find a name with libm.a or libm.so, either one of them. Whatever it can find, it will find that. Okay, and then -o hello world.out. Now you see that it didn't give me an error. Why? Because when I said -l switch, it is able to find the library file with libm.a or libm.so. I think the Ubuntu operating system first tries to find the .so file, and then if it is not able to find the .so file, then it finds the .a file. Okay, so this is how my executable is generated. Right, so this is what my executable looks like. So here it is. So this is my executable file. Now this executable file is also a binary file, right? Like a .o file. The only difference between this .o file and this .out file is that .o file did not have the addresses for the functions that we were calling, if they were library functions, because the library was not provided in the assembling step, right? In the linking step, we provided the library information. So when it created the executable file, that is where it found out where the functions are. Okay, and then it would have linked those functions in my executable file. So what I can do is
Sir, but the library part is done by preprocessors, no? So what is the use of linker then?
No. Preprocessor only takes the header file. See, I explained to you in the last lecture that the header files have only the forward declaration. It doesn't have the function code in it. The header file does not have a function code in it. Remember, I showed you the header file stdio.h. So let's do locate stdio.h. Sorry. And let's open this file. Now, if you look at this scanf function, do you see the code of the scanf here? Is there a code of scanf function here?
Yes.
No. Where is the curly bracket? How do you write function? How do you write function? You write function like this, right? You have to have the function signature. You have to have the curly brackets, and then you have to write the code in between. No.
Yes. Sir.
How do you write the function? This is the way you write the function. This is called a definition of the function. Remember, I explained to you there are three things in the function. One is function signature or function header. Second one is the function call. Third one is the function definition and the function forward declaration. Right? So this is the definition of the function, meaning the actual code of the function. What the header file contains is only this part. Only this part. It is only the declaration of the function or the header of the function. It doesn't have the code of the function. Are you getting my point?
Yes, sir.
So if the header file doesn't have the actual function code, only thing it is telling the preprocessor and the compiler that this function is available somewhere, where preprocessor and compiler does not know that, does not take care of that. It is a job of a linker program, linker utility, to find that where this function is located, in which object file it is located, or which library file it is located. If it doesn't find the function even after linking step, then we get an error like this, what we got earlier. Let me just run the step without -lm switch, and you will know what the error is, right? This is the error that linker throws out. So basically what the linker did is that I tried to find a POW function, okay, in all the object files that has been provided to me, but I couldn't find the POW function, the code of the POW function. Therefore, it is saying undefined reference, meaning that this function is, reference to this function is undefined. The address of this function is undefined, and I cannot actually find out what is the address of this function that I can include in my in my function call. So, and you can see the error is coming from LD program, LD, right? LD is for linker. So LD is telling you, the linker program is telling you that this function is not, I'm not able to find out, right? But as soon as you provided the library where the actual function code is, this is where the actual function code is in the library file, then so the preprocessor expanded, compilation said that, okay, I will try to put some dummy address in the POW function. Assembly step also did the same thing. Now the linker step has to find where the actual reference is, where the address of this function is in the memory, right? And then include that in the executable file. And that is what, in order to do that, we have to provide the library file if the GCC compile or the linker is not by default able to find it. Clear to everyone? Okay. Now let us disassemble this executable file also, right? Let us disassemble this executable file also. So I'll say obj dump minus, let me actually do -g here so that we get an additional information. And then we will do obj dump minus, what were the switches, minus the ms. So when you look at this file now, this is the unassembled or basically reverse engineer file for your executable file. Okay, for your executable file. Now what we have to do is we have to look for the main function first, right? Because that is where our R code is, right? So you can see that the preprocessor took care of this one, and now this is where my main function starts. Okay, so now if you see, the printf is over here. Okay, and the printf, now you can see there is a difference between the other assembly code and this assembly code. It has the actual address value here. 1070. If you recall, in the other assembly code, it did not have that particular value. If I have it open, I can still look up. Where is that file? Here. Right, so it did not have the actual address value. It just says something 24 main plus 24. So it is saying somewhere it is loaded in main plus 24, but it doesn't know. Here also it is saying main plus 41. Here also it is saying main plus something, right? But it doesn't actually have the address. Whereas here it actually has the address. So it says that you have to go to this location where you will find the printf function. Okay, and if you go, you can see these are the addresses, the memory addresses. And if you go to 1070, there is a 1070 address over here. 1070. There is an address called 1070 here. And you can see that it is saying this. What does it mean? It means that printf function, you have to jump to this location in the memory. You have to jump to this location in the memory where the printf function is located. And the printf function, the code of the printf function comes from the glibc library file. glibc library file, which has this version 2.2.5. Okay, so it is telling me that the printf function is located in this area. That is where I would be able to run it. Okay, now if I go back to my main function, it says that a POW function is located at this address. And when I go to that address, which is over here, then it is telling me that my POW function is located at this address and it is part of this library.
Yes, sir, what is this font over here, indent? The code after pound over here.
Sorry?
So what does the code after the pound sign denote over here?
Which pound sign?
There is hashtag sign, is there? No, hashtag sign.
No, that basically is saying this is the function name and where it is located. That's all.
Okay, sir.
So what I'm trying to say is that if you look at this assembly code, it actually has the actual address where the function is located, right? Where the actual function, and also one thing you would notice is that if you go here in this assembly code, here you see it says call 24. So this one is a printf function call, right? It says call 24, and then here is the 5e, right? Here is the 5e. Even though it is the same printf function being called here and here, it has a different value. It has a different value because it doesn't know that this is the same function we are calling. Whereas if you go to this final assembly code, you will notice that it has exactly the same address value because linker knows that these are the same functions. Here also we are calling printf, here also we are calling printf. Getting the point?
Yes, sir.
Right? So this is how your final executable is created, and this is the equivalent binary code or hexadecimal code for this binary for this assembly code, and this is the assembly code equivalent to your C program. So this is exactly how your code, your C source, gets converted into the executable file. Now, what we have done is we have looked at only single C file. Right? We have not looked at multiple C files where we use our own functions and link them together. Right? So let us do one thing. I believe it is there in the next slide, but yeah. So you can use a multiple C files and you can use your own header files. These multiple C files can have the functions calling between these C files and so on, and you can do those forward declarations over here. So we have already considered that example earlier in learning about the header files. So we have a file one main.c, right, and then file two other.c. So here we have the global variable, here we have the function declaration, this is our own function, right? It's not a library function. And then this is the header file that we are using, right? So now when we do the compilation of these, there will be separate .o files. There will be separate .o files. Now .o file is only created for the C file. Remember that. It is not created for the header file. Header file is only used for forward declaration, right? So header file is not a source. Okay, it is only included in the other C file. So therefore, you will not have the .o file for the header files. So what we can do is we can create the .o file from these files, and then we can run the linker steps. Okay, so in order to do that, what we will do is, sorry, I have to go back to. So we say GCC minus G, I'm going to use it so that we get an extra information in the executable file. And then I'm going to run the first 3 steps, right? Pre-processing, compilation, assembly. And then I'm going to create a .o file for file1.main.c. By the way, you can provide multiple C files in a single command. You don't have to do separate compilation for multiple C files separately. So I'll do this also, right? So file2 other.c. So I'm going to compile both these programs to get, one at a time, but in a single command using a -G and a -C switch. So when you look at it, now you will see that there are 2 .o files over here, right? There are 2 .o files over here. Now, using those 2 .o files, I can actually create the, I can run the linker step, and I can create the final executable file. So to do that, I'll say GCC file1_main.o file2_other.o -o file1_main.o. Now, since here we are not using any library function which are not available in the standard or default library files, we don't have to provide any -L switch, because I'm not using a power function or any function that is not available in the standard library file. Okay, so I don't need the -L switch here. Now, using this output file, I will create the assembly file. Okay, so obj, let me just go back. It has the command, so I'll just use that command here. Okay, and let me open okay, so now if you see this, so this is my main code, right? This is my main function coming from the first object file, the file1 main object file. Okay, and you can see that there's a variable initial variable value which is changed using this move command. There is a printf function which I'm calling here. Again, it is called at 1060. This is the printf that is called here. So the printf function calling is done differently in this case. The reason being that here we don't have passing of the parameter, whereas here we have the passing of the parameter. So passing of the parameter in the printf is handled differently than the constant string. Okay, so that is why there are 2 different things here. And then you can see that there is a call of function f1, which we have in our main code, right? And that call is over here. Now, if you go to this address 11CA, 11CA is where the f1 function is. So 11CA is located over here. So you can see that even though my function f1 was in a separate object file, file2 other.o, right? When I created an executable file, what did it do? It took the object code of that function and included in my executable file. And this is the equivalent binary code / assembly code for that function. So here is the command for each, here are the lines for that function code, and it is including that over here. Right. So basically what is happening is that even though I have multiple object files, all the code from all the object files are included in a single executable file by a linker, and linker is then able to map these addresses in the final executable file to say that the function is located at which place. Is it clear to everyone? Any questions? Clear to everyone? Am I audible? Am I audible?
Yes, sir. Yes.
Okay. Okay. All right. So we are coming to the library file, and again, this is a larger topic. So I think I'll stop here because we won't be able to go a lot further. I'll have to explain to you a lot of things for the static and dynamic library. So we'll start the library functions in the next lecture. But if you have any questions about what we covered so far today, let me know.
Hello, sir.
Yeah.
Sir, if we are not doing this linking process like separately by ourselves, will GCC do it for us by itself when we just compile things?
Yes. So for example, if you don't provide -C switch, everything is done, all the 4 steps are done together. Okay. So if I just want to create an executable file, I don't care about what all the steps that GCC follows, right? I just want the executable file. Then all I have to do is hello world.c -o hello world.out. So it will directly, okay. So I have to provide obviously -L switch here because again, it is doing all the steps, right? So I have to say this. And so it takes the C file and it finally converts it into the executable file directly. And then I can run my executable file directly. That's it. Okay.
Yes.
So this is done. And same thing you can do with multiple files also. So I can say GCC file1 main.c file2 other.c -o file1 main.out, and that's it.
So since we have not included the hashtag math.h file, we need to do that linking process. Is that right?
So like I said, only the functions that are available in certain header files, like stdio.h, like strings.h, like stdlib.h, those functions are by default linker will try to find. And for that, you will not have to provide a library information. Okay. But for the specialized, for other functions, right? Like math.
Like sir, if we include math.h in the code itself, if we specify header file.
We have. That is why it is asking for this information. Okay. I think you are still missing the point. What you are missing the point is that the math.h only has the forward declaration.
Oh, so, yes. So we need to specify where the function.
Where the actual function code is, that is still needs to be told. See, the math.h is already included here.
Okay.
In your source file, math.h is still included. But this one only has the forward declaration of the POW function. And if it is not still coming to you, let me go and locate math.h And let's open this file. POW function should be here. It's not able to find. Which math.h it is using. I'll have to see that. Okay, let me do that. Grab. Anyway, I guess I'll have to find where that function, which header file is being used, because since there are multiple header files, multiple math.h files, it will be using the one which actually has the forward declaration of this function. Okay, so I think it is this one. User include C++ C dot. So this is the function. This is the file probably it is using for the POW.
Okay, sir.
So what I'm trying to say is these only has a forward declaration, and then the actual code is in that libm.a library file or libm.so library file. Okay?
Yeah, okay.
So the linker will only deal with that library file or the .o file. Any other question?
Sir, I am having a doubt, sir. Sir, while we were linking the hello world.c file, means it was having a header hello world.h file, right? And in that hello world.h file, string.h file was included.
Correct.
So do we have to link that string.h file also over here?
So string library file, the string functions from the library file is automatically linked when the linker runs. Similar to printf and scanf functions, right? So we don't have to link any library for the printf and scanf functions, because whatever functions are there in the stdio.h, those functions are by default linked.
If instead of string.h file, if we are having method.h file there also, then
also we have to link it. Yes. So I can show you that. So let's say I remove it from here. I change this over here to this, and then let us compile the code again. So GCC file1 main.c file2 other. Sorry, was it hello world that we modified? Yes.
Yes, hello world.
Okay. C. So you still get an error, right? Because math header file is included in that H file, and that H file is going to be expanded in the pre-processing step for this source file. So eventually you still require that. Now, unless you are not actually calling the function, so even though you are including the math.h, but let's say I don't actually call this function. I comment this line out, which means that I'm actually not calling this function, right? If I don't do that, then obviously I don't require the linking step to do, because the POW function is not even referenced in my code. Even though you have included the header file, but if the POW function is not referenced in the code, it doesn't require to find that code. It doesn't require to find the function code in the library file, in the linking step. So preprocessor will still expand the header file because we have told it to do so. But then when the linker step runs, linker will never find any function from that header file that that is actually being used in your source code. So there is no need for a linking.
Yes, sir. Got it, sir. Means, sir, the library functions that are included in the header files, that also should be linked while linking.
Okay. What is the difference between header file and the library file? You tell me that.
No, sir. My question is, in the header file, if you are including any other library files, so we have to link that. So we have to link that.
Yes.
That files also over here. That library files also.
Yes. So when we do the threading, when we run the program, when we actually learn the threading part, we will use a library called pthread, right? So for running any of the threaded programs, we will have to include a threading library, because the threading library is not by default linked in the GCC command. Okay. So what I'm trying to say is that why the functions such as printf, scanf, string functions that we use, we don't really require to include the library file in the linking step, is because the GCC linker, the LD linker by default will be linking those functions automatically without us telling which library file to go to, because it knows that these functions are very widely used and therefore it will automatically include them. Understood?
Yes, sir.
Okay.
Hello, sir.
Yeah.
Sir, when I execute the command in order to run the file, I am not getting error, even if I don't use -lm switch. But
For
my
which?
code include. Okay, so my basically C file includes the math.h. It uses basically library math.h. But even if I don't use -lm switch, still it is not giving me any error.
But are you using any of the functions in
Yes,
your
yes,
code?
I am using power function, by the way. Yes.
Then I think there's something wrong happening there. It would give you an error. Are you using -c switch?
No. So basically, I am not using any switch. So I have executed the row command basically, like gcc test.c -o test.out. That's all.
Well, I mean, as far as I see, the point is, as long as the library files are included in the linking step, you will not get an error. When the library files are not included in the command line, then it will give you an error. And by default, only the functions that are generally there in the stdio.h, stdlib.h, string.h, those functions are generally included in the linker. But generally speaking, the main ones, the math ones and some of the other ones, they are not included. Now, so you will have to actually check. Maybe I think in the next lecture, I'll show you that which library files are by default included in your executable program. And so you will come to know. So I guess let us wait for another lecture where I will show you how to look for the function code in which library the function call is available, and then whether it is linked by default or not, right? So once you find that out, there is a LDD command for doing that, which I'll cover in the next lecture, this LDD command. So it may be possible that in your system, the math.so file is by default included. You can see that in my case, it is not found. Right? In my system, it is not found, but maybe in your system, this is already found. If this is already found, then you may not have to use the -l switch.
Okay, sir. Thank you.
Yeah. All right. Thanks, everyone. And I hope there's no other question, right? Okay. So thanks everyone, and we'll talk to you next week.